Okay, so when IC is going to increase, the process will become cumulative, and enormous amount of heat will be coming out of your transistor, and that will ultimately destroy your transistor. So a slight change in temperature will completely demolish your circuit. So if I don't want that to happen, then proper biasing of your BJT is required. So in addition, the Q point can shift due to temperature changes, and transistor can be driven into saturation. So because of all the parameters which I told above, the Q point will be gradually shifting and the device will be going into saturation. So when normal amount of current is flowing, the device is in active region. When enormous amount of current is flowing through a BJT, it is going to be saturation region. Okay, so when the device is going to saturation, it will stop amplifying, and heat will be very high. The amplifier function will cease, and the device will be slowly in the mode of destruction. Okay, so and one more thing which will change your performance of BJT is VBE, and VBE will depend on temperature. So it is around 0.6 to 0.7 volt for silicon, and it is 0.2 to 0.3 volt for germanium at room temperature. So room temperature is 27 degrees Celsius. That is a standard room temperature. So when the temperature is going to increase in countries like India, this VBE will also be slightly higher. So if VBE is higher, Q point will again shift. So we have to design a proper circuit which is going to handle all these drawbacks for me. That circuit is called as my biasing circuit. Okay, so the three parameters which are culprits in the working of BJT are beta, current gain, VBE, the emitter base voltage, or I can say it is the forward bias voltage in the base emitter junction, and last one is IC naught. IC naught is your reverse saturation current. You can see here, I'm just giving you a graph. You can see VCE versus IC. I'm drawing the output characteristics, and you see here, initially my Q point is here. See, this is your cutoff region. This is your saturation region. So initially my Q point is here. As the current is slowly increasing, you see the Q point is slowly moving towards saturation. The Q point is going to move upwards, this is saturation. If the Q point is going to slowly move downward, it is going to be cut off. If the Q point is exactly in the center, it is called as active region. So in this graph, in this straight line, if the Q point is exactly in the middle, it is going to be the active region. Even slightly it is going up or down, it is not active. It is going to be going towards saturation, or it is going to be coming towards cutoff region. So you can see how you can visualize clearly how the Q point is going to change the operating conditions of your device. Okay, so that is why I need to maintain this Q point exactly in the center. So if that has to happen, I have to design effective biasing circuits for this to happen in my BJT. Okay, so see, the IC naught will increase double every 10 degrees, but this VBE will decrease for every 2.5 millivolt per degree Celsius for both silicon and germanium. So VBE will start decreasing. So if VBE will start decreasing, the current will start increasing. Okay, so that is why we say that whatever parameter depending on temperature is going to increase or decrease, my Q point should exactly stand steady in the middle of this graph. This is output characteristic graph for common emitter amplifier. So when you draw this line, you have to have the Q point exactly in the middle. So which means my voltage should be exactly half, my current should be exactly half. So that should be maintained. So they established this operating point. We are going to have a lot of circuits which are going to do this fixing this operating point in my BJT transistor. Okay.